AC 111 Lecture 3 Set 5 FPGA and ASIC Digital Design Flow. When we program the field programmable gate logic, we usually use a computer-aided design or a CAD tool to ease our life. We are not going to go and program each and every of those LUTs that we just described. So typically what happens is that we enter the design using a hardware description language, such as the system Verilog we are learning in this class, and then we simulate it because it's not always the best to go and try to synthesize it into a piece of hardware and see how the hardware looked like before we don't have a simulation model of the bigger system. And then after we synthesize it, and the synthesis is really a compilation of the high-level description code into bit-level logic, and then this whole compilation gives us the configuration bits that go into programming those LUTs that we just saw, and then we're ready to test the design. This is a high-level picture of what happens. Typical designs have much more detailed and involved design, as you will see here. In particular, when we design a big system, first we start from a system specification. Typically, a system design team is involved in making the system specification and architecture specification at the system level for that. Once we have that, we go through this design for each of the designs in microarchitecture specification. So we define what should those small blocks that make the system a bigger working system look like. And this microarchitecture, we typically define each of the microarchitecture units using hardware description language, and then we go through the digital design and we synthesize it into a net list. At this point, we have a functionality at the netlist level, so we could verify the design at the functional level. We could also do some post-synthesis simulation on this logic design in terms of a netlist and get some ideas or back-of-the-envelope calculation about how this would perform in real life. It would not be until we go and actually put this into a physical device, we actually generate the bits that program those LUTs and interconnects, that we get a real understanding of what this will perform on programmable hardware. Here, the implementation really means that we're going to map that piece of netlist into the device, and we're going to place and route it. So we are going to place the different logic blocks and maybe change the placement. This is an iterative process, and we're going to route the interconnect between them. And then we're going to generate the programming bit stream after certain optimization and iteration that goes into programming the actual FPGA, then where we're going to run software on the top of this piece of hardware. So the synthesis by itself, where we're trying to synthesize or compile a piece of HDL code, is a multi-step process. We first check the design and the resources associated with it, then we optimize it, and then last but not least, we map it to the technology, which is really the fabric of FPGA. So the design check is typically the associating of the design to logic cells and blocks. This is typically done in simulation. The optimization is to reduce logic, eliminate redundant logic, and then make the design smaller and faster. This is also typically done in simulation, but this is not a one-time process. In fact, we do optimization in each and every part of the design. Last but not least, we go through an optimization and technology mapping, where we take this reduced and optimized design and we map it to a technology, and we go iteratively through this process to get a real actual physical design and the net list for the design. Now, this was the steps of a design for field programmable gate array, or FPGA. As we've mentioned earlier, what we learned in this class with System Verilog, you could also use to design an ASIC chip. And ASIC chips, in terms of the logic description, the description looks very similar in System Verilog, but once we specify the design, the back end or the physical fabric that is implementing this is very different. If you remember, in FPGAs, we had that programmable logic using those MUXes and LEs and programmable interconnect that connected those. In ASIC, we're going to hardwire every function to a defined logic gate, and the wires are all defined after we come from fabrication facility, a chip comes, it's super hard to change anything, if at all. There's just little possibility maybe to cut some interconnects, and that's even a costly process. But for all what it matters, you should assume that the design that you send to a fabrication facility is final, and what you're getting is what you would get from that file that we sent. So the front end for FPGA and ASIC are pretty similar in the sense that both of them are using system Verilog, and the system Verilog gets optimized and translated into a netlist, or just the logic netlist. But then the back-end design is pretty different. In FPGA, we after we got that logic description, when we would go and put it, map it to LEs, LUTs, and program interconnect, and here we're going to take it to standard cells, place and route it. And one thing that is super important is there are design rules that are defined by the foundry that should be very closely followed by the designer, and many times these designs, because they're in so small scales, may violate those. So this is called the DRC check. That's an iterative process to make sure that DRC errors do not happen. There's electrical rule check, because what we implement that gets translated to a physical entity. For example, there's a minimum size for the wires or other elements that should be satisfied, and then we make the schematic, and we make what is called at the end a GDS2 file, which is sent to the fabrication. And after something comes back from fabrication, even then it has to be tested, even if it was tested in simulation, which is typically the case. And then we need to validate things post-silicon and do the software. So in effect, the front end is very similar. We use the HDL synthesis system specification. The back end is very different. And if you go work in a big company that uses these designs, then you should be worrying about that, because that is something that is very specific to the processes that are offered by the foundry, and take a little time to learn how to optimize and work within the DRC and LVS and verification tools. The front-end design, as I mentioned, is similar. We just get gate-level code, and the back-end is different. And in this particular case, the timing information is coming from the technology files. If you have technology files that are standard cells, such as AND OR, it's very different than what we get from, say, an LUT or programmable logic. And that's where the back-end design and how you simulate it also differ. So the simulator should have a notion to what it is going to map to get you back of the envelope calculation, even at the higher level for timing power and other things that we are trying to optimize. In the next set, we will be looking a little further into simulation and synthesis before we wrap up, and we will be focusing on FPGA from now on in this class.